First of all, we're just going to talk a little bit about what sensors are and how you use them in general. And then I'm going to show you an example of using sensors to make a little ball bounce around the screen. One thing you have to be really, really careful about, never make any assumptions about what sensors are on a device. There's some sensors like an accelerometer, which are on almost all the devices out there, but then once in a while you stumble on one that doesn't have them. Never assume they're there. You're always going to want to ask the sensor manager to get a hold of things. And if you don't get one back, fail gracefully on it. Now, of course, if your application absolutely requires that functionality, you're going to have to report to the user, sorry, I don't have this. But a better way to do that would be to use a uses feature functionality in your manifest so that the user going to the Play Store wouldn't even see your application if their phone doesn't have those features that you need. Other than making assumptions about presence of things, keep in mind that when they're making phones, they're usually going for the chip for the main processor unit on there is usually their most expensive piece. That and some of the other parts. Maybe some of the other functions in the application, in the phone itself. A lot of these sensors, when we're talking about the accelerometer, a gyroscope, light sensors, magnetometer, things like that, these things are super, super cheap. They usually go for the cheapest. They don't always go for the most accurate because they're really not looking for professional grade equipment here. This is consumer grade stuff that they're trying to get there so that somebody can tilt their phone and make a car drive. They're not worried about how precise that is. So keep that in mind that a lot of these ones are not going to be super, super accurate. Talk about a couple of sensors in particular, just to kind of give an idea what's going on. But let me first explain what an accelerometer does here. Think about having some springs or hanging scales. So if you had a hanging scale that you might use to weigh a fish, for example, the hanging scale is going to have a little ball on the end of it. And depending on how you're holding that, gravity is pulling that ball down. So if we had all of our, and these accelerometers are actually three-dimensional, so there's actually two more than you see here. There's 6 of them. Think of it as if you have the device perfectly straight up, you're going to get a measurement of 9.8 meters per second squared as our acceleration. It's going to be negative because you're pulling it down in this case. As you start twisting the device, you're going to start getting some different values based on the vectors that are being used for pulling that weight. So if you perfectly balance it, you might get, 6.9 components of the gravity pulling down there. If you jump when you're holding the phone, theoretically, there should be a point when you're weightless. And so everything should be reading 0. In real life, probably not going to see that. But keep that in mind, different types of motions the user does. This is measuring the linear acceleration. And that linear acceleration value includes gravity. So gravity's got to pull, but if the user moves the device in different directions, you're going to see the readings from those different directions as well. The most common thing that people use this for is for tilts. So if you want to have, maybe you're writing an application that has a little labyrinth maze where you have the ball that you're tilting the screen to try to make the ball go around a path in the labyrinth. You might use an accelerometer for that. The magnetometer is a compass. And one of the things that's really important to understand here is it's a 3-dimensional compass. It's not just a 1-dimensional compass like you might hold in your hand. And this is important because it depends on how you're holding the phone. Somebody might be holding a phone straight up if they're looking at Google Maps, and you still want to see that compass value going straight through the screen. Some people might hold it flat on their hand like they would a traditional compass if they're using a compass application. So it really depends on which direction you're holding things. One thing to be a little careful about is in a device like a phone, you've got a lot of different magnetic fields involved. And depending on how well the phone was built, there might not be some great shielding inside there. And so you might be getting a lot of noise from the magnetic fields around you. And again, some of these are really super cheap components and they don't calibrate super well. So if you ever are using Google Maps, you'll notice this little cone that it displays. The wider the cone is, it's trying to tell you that its accuracy is pretty low. So, and the cone kind of points in the general direction you're facing. Some sensors that we have on the device are actually fused sensors. They're actually computed virtual sensors, like an orientation sensor, for example. And there's a bunch of algorithms defined to take the inputs from several sensors. Like you might take the input from the accelerometer, the gyroscope, and the magnetometer to try to see what your actual orientation is. And using the three of those together, using some smart algorithms, you can get a pretty good orientation out of it. Now, if you're interested in what's going on behind the scenes in this algorithm, there's a great talk I saw on YouTube called Sensor Fusion on Android Devices or Evolution in Motion Processing. And it's pretty old, but a lot of what these people did, David Sachs is the guy who did it. A lot of the InvenSense algorithms are actually being used in the Android core now. Originally, there were algorithms that they published that, in their own libraries, but they worked with Google to actually integrate these, and they work fantastically. So there's these virtual sensors. You might have like a gravity sensor, which is one that tries to pull out the gravity component from the linear acceleration from the accelerometer, or just pull out the linear acceleration itself without gravity. Rotation vector is probably the most common one that people are going to use for this, where you're trying to figure out your orientation. For example, if you're using the Google Sky Map application, where you point it up in the sky, it's trying to show you as though it's a window to which stars are out there. And depending on where you're facing, it tries to line that up pretty well. And depending on how well calibrated the device is and how accurate the sensors are, it can be a great application. Sometimes it can be off a bit, it can be a little bit distracting. So let's take a look at a quick example of a little application to use the accelerometer to make a little puck go around the screen. And so this is a little composed version of a previous example that I had. And I'm starting off by having just a chunk of data representing a puck on the screen. And so this chunk of data has the color of the puck, the center location, the radius, the change in location, so the delta x and delta y at each time step, and then the current acceleration. So the accelerometer is going to be driving the current location, the current acceleration. And then at certain time steps, we're going to update the speed that we're going, which is the dx and dy, and we'll also update the center based on the speed. So that's kind of how this goes. Now, this is not an accurate physics model, but it works pretty well. I mean, it gives a pretty decent fake approximation to physics of a ball bouncing around. It's a real simple one. Just keep that in mind. So what we're going to do here is we need to go ahead and get our sensor manager and the gravity sensor. To do that, we're going to call get system service on the activity saying I want the sensor service and just cast it to a sensor manager. This is very similar to how we did our API to a service. So how we defined in AIDL that alien service that we were talking to. What this does, this sensor manager is essentially that service interface to the sensor service on the system. So we're going to get that sensor manager, and then we can ask the sensor manager to give our default gravity sensor. The gravity sensor is doing the just figuring out the gravity component of the accelerometer. What's nice about that is if the user kind of moves quickly to one side or the other, it should factor that out. So once we have those, we're just going to do our little user interface on this. So this user interface, I'm starting off saying, let me get the current density so I can do some calculations of dPs to pixels. I have a little text box at the top that's just going to display some status. So in here, I'm just having it display the current rotation of the device and the X and Y acceleration values. I'm going to use this box with constraints composable. And what this guy does, let's split him up a little bit there. There we go. What this guy is going to do is he makes available max width and max height, min width and mid height. So the constraints that were used for this guy are exposed so we can look at them. And that allows us to see the current width and height of this box that's inside the column. I've also set this up, let's see, so the text is filling max width. I should really have this say fill max size after that. So it'll just fill up the rest of the screen. I believe it does. That's probably the default inside there, but it's nice to actually specify that explicitly. So I'm going to grab the width and the height by converting the max width and max height from dPs to px. And then I'm going to figure out the radius of the ball. I'm just going to make it be 1/10 of whatever's smaller, the width or the height. I'm going to create a puck info. So here's my initial puck info. I'm going to put the center at, radius times 3, radius times 4 for the X and Y. Set the radius and set the color to red. Store that in a mutable state of that I remember in our composition. So this is our little bucket that I can change the puck info. Whenever I put a different puck info inside there, I'll recompose. That's what's going to trigger our actual animation, the drawing on the screen of moving this ball around. Here's an interesting part. I needed a way to listen to the sensor events. So I'm going to say, hey, let me get the sensor manager reporting the sensor events to me to tell me what values are changing on the fly. But I also need to make sure I dispose that. And what I did in the previous example is I overrode the onStart and onStop functions in the activity. And I had the set up the listener in the onStart, the remove the listener in the onStop. And that worked great. But we're doing compose now. We can actually do this inside the compose framework. So we use this thing called a disposable effect, which performs everything except for this onDispose block when we're initially composing things. So we run this once. So I'm creating this listener and registering it. I'll go into the details up here in a minute. And then once this is being removed from the tree, we call the onDispose part, which is just unregistering it. So that's actually fantastic. It makes it nice and easy to have in one spot the add and the remove of the register and the unregister of these listeners for us. Let's take a look at what this listener looks like. So this sensor event listener has two functions in it, on sensor change and on accuracy change, which means we can't just use a lambda, unfortunately. We could create a little helper object that implements this and define a lambda that creates the helper object passing the lambda in for on sensor changed. I didn't want to get into that detail, but this is actually a good example of what you do if you have an interface that you have to implement multiple functions. So we're going to use the object keyword to create an instance of some class that implements sensor event listener. And here's the details. It's the same kind of thing as you'd have an anonymous inner class inside Java. So our on sensor change is actually getting the sensor event that has the information we need. Unfortunately, we have to take into account the rotation of the device as well and fix up those values based on the rotation of the device. So we're using this default display guy that I defined up here. Where is he? Which is window manager.default display. This is deprecated, but the new function for it is only in, I believe it's in Android 30. So we could put some logic in here to say, if I'm in API 30 or later, use display, otherwise use window manager default display. I didn't want to do that right here. I wanted to keep it simpler and still use default display, which will still work for now at least. Okay, so once I get that, I can use the rotation information from that to tell us which angle the user's holding it. So rotation 0 is the natural way you'd be holding the device. For a tablet, it's going to be for at least the tablet I've got here, it's portrait rotation. Rotation 180 is exactly upside down of that. So if they're holding it upside down, 90 and 270 are when it's 90 degrees from each of those. And what I'm doing inside this is when the rotation is a certain value, I'm creating a pair with two values. The pair has the component 1, component 2, component 3, and so on functions. Component 1 will get the first one, component 2 will get the next one. And because I have those component functions, I can use a destructuring declaration up here. And I like this because then I didn't have to have two separate when clauses. So it's going to pull these values out as X value, pull this one as Y value. So we're pulling these, fixing them up. I don't want to go into the math behind that. Let me talk a little bit about where you can find information like that. If we look for Android sensor, we have this sensor class here in their documentation. Actually, it's sensor event, I think is what I want. Sensor event. Yeah, this is the one I wanted. This actually is one of the best documentation that I've seen in the Android API. And so what the sensor event does is based on what type of sensor we're dealing with, it returns different types of data. And they talk at first here about the X and the Y axis. And the reason that I have to actually convert those is that these are fixed on a device. When you're doing the rotation, you're going to have to reinterpret X versus Y based on the orientation of the device. So we'll see here that on this device, a phone, the Y-axis is the normal up and down for how you'd normally hold the phone. The X-axis is the normal left to right based on how you're holding the phone there. When you rotate the phone, you want to use the Y-axis as the X-axis. But notice if I rotate this 90 degrees to the counterclockwise, the Y-axis is going to be pointing over here to the left, which is backwards. So I have to use the negative of that Y-axis as the X value. And the X value is pointing up, so I just use him normal. So depending on which direction you're holding the phone, you have to adjust the values there. Now we'll see in other spots down in here, they talk about the different values that are returned in this little array of values. So if you're asking for accelerometer, here are the values. It's the acceleration minus the gravity on the X, Y, and Z axis for type accelerometer, kind of like I displayed in that example up front there. And then they talk about the magnetic field, the gyroscope. They have little chunks of code in here. They did a great job on this piece of documentation. And they still could do more with it, but compared to other docs that I've seen, they explain things pretty well in here. So if you're really looking to deal with the sensors, take a look at this documentation for sensor event. It's a good thing to look at. So that's explaining why I'm doing this manipulation of things to actually get values to come up there. And I actually had to flip the X values based on how I'm using it on the tilting of the application. So once I've got that information, I'm just updating that text on the screen. That text is in that remember block. And then I'm updating my puck info by copying the existing puck info. So the only thing that I want to change is AX and AY. This copy is given to us by the data class there. So when I say data class up here, it creates a copy that has all of these values in that copy, and their optional values or their default values are their existing values. So you can just replace which pieces you want by doing a copy like this. That's going to update it, which should trigger redrawing things on the screen. So that's our whole disposable effect there, doing our register and deregister of that sensor event listener. So now I want to have a little coroutine running that's going to move the puck around the screen. So what I'm doing inside here, I'm just calling launched effect to start up a coroutine at the beginning. And I'm just going to run this sucker forever until it gets canceled. Because this launched effect is inside of this composable, when this composable goes out of the composition, it'll automatically cancel this coroutine. It's really nice that way. So we'll run this thing through, pause for 50 milliseconds, and then tell the puck to move. And this move function is going to do the calculations based on the acceleration, which was set here, and the current velocity that we're doing, and where it currently actually is on the screen. So final thing in here is the actual surface that we're drawing on, just putting the background color in, and then doing a puck. Let's take a look at that puck real quick. Then we'll come back to the move so you can see what that looks like. So the puck is real simple. He's just a canvas that's drawing a circle. That's it. So we use the puck info to get the color, the center, and the radius, and boom, we're drawing that on the screen. So he's nice and simple. Now the most complex thing in here is this move, which really isn't that complex. And this is where I'm faking the physics. And it's kind of amazing how simple the physics was to fake here. Well, one thing I should point out is that I multiply these values by 5. That was just a gut feel. So as I was playing around with the application, I tried different multiplication factors on the acceleration that I'm getting from the device to see what kind of felt right. And multiplying it by 5 felt like the right kind of value for me. So the movement, what I'm going to do is I'm going to say my new delta is going to be add the acceleration to delta x. My new delta y is going to be add the vertical acceleration to the delta y. So I'm going to basically change my speed based on the acceleration. And Yeah, if you're a physics guy, don't give me grief about this. When you see this run, it works good enough. Then for the center is going to be take our existing center and add that new velocity. Then I want to check to see, am I within the bounds? And the bounds that I want to do here is I want to make it look like the ball's bouncing off the edges of the screen. So I'm saying, look at the center, and the center has to be at least radius away from the edge, and at most width minus radius against from the right edge. If it's not in that range, I need to do something special for it. So what I'm going to do is change the direction that the velocity is going by flipping it over, by negating it. So this is going to make us bounce away from the wall. But I'm going to divide my speed by 2 just to kind of slow it back down. So I'm not going to have a perfect elastic collision here. See, I do remember something from physics. Then for my actual location here, the center location, I want to coerce it between radius and width minus radius. So this just makes sure that its lowest value is radius and its highest value is width minus radius. This coerce function is fantastic. It reduces your code quite a bit. And then we do the same kind of thing for the y value. Once we have all those, I'm going to make a copy of the puck info that we're doing, just changing the velocity and the center location. That's all we need to change. So that is all of our code. So let's go ahead and run them on there. And right now I'm holding this device straight up like this. So I'm in that mode. You notice how the ball kind of bounces there. I'm going to tilt it forward somewhat, just kind of lean the ball down. And then I'm going to lean it to the left and to the right and to the left, and maybe down over here, and kind of move it around. And you'll see that it's okay. I mean, it feels like kind of a heavyish ball. It's not getting a lot of bounce off the edges, and then it settles pretty quickly. But it gives a pretty reasonable-ish feel for moving this thing around there. Okay, so boom, there we go. That's that. Now, if I rotate the screen, I'm going to rotate it counterclockwise, 90 degrees. Now we'll see that I'm still getting the same effect here, moving around. And depending on how much I tilt, if I kind of slow down my tilt, I can get the acceleration to be pretty minimal. Or if I do it really fast, just completely slam it from one side to the other, I'm going to get really fast acceleration out of it. And I can go back up to my portrait mode there. So that's a nice little example of using the sensors on the device to put some animation into the application.